In this unit, we will discuss the concurrency control problem, which occurs when multiple transactions submitted by various users interfere with one another in a way that produces incorrect results. We will start the unit by introducing some basic concepts of transaction processing. Why concurrency control and recovery are necessary in a database system is then discussed. The concept of an atomic transaction and additional concepts related to transaction processing in database systems are introduced. The concepts of atomicity, consistency, isolation, and durability, the so-called acid properties that are considered desirable in transactions, are presented. Concurrent access to data. Concept of transaction. The very first concept that we introduced to you in this unit is a transaction. A transaction is the execution of a program that accesses or changes the contents of a database. It is a logical unit of work, LUW, on the database that is either completed in its entirety, commit, or not done at all. The transaction has to clean up its own mess, known as rollback. For recovery purposes, a system always keeps track of when a transaction starts, terminates, and commits, or aborts. Hence, the recovery manager keeps track of the following transaction states and operations. Begin transaction. This marks the beginning of transaction execution. Read or write. These specify read or write operations on the database items that are executed as part of a transaction. End transaction. This specifies that read and write operations have ended and marks the end limit of transaction execution. Commit transaction. This signals a successful end of the transaction so that any changes, updates executed by the transaction can be safely committed to the database and will not be undone. Rollback or abort. This signals the transaction has ended unsuccessfully so that any changes or effects that the transaction may have applied to the database must be undone. In addition to the preceding operations, some recovery techniques require additional operations that include the following. Undo. Similar to rollback except that it applies to a single operation rather than to a whole transaction. Redo. This specifies that certain transaction operations must be redone to ensure that all the operations of a committed transaction have been applied successfully to the database. Let's look about interleaved concurrency. To avoid excessive delays, concurrent systems execute some commands from one program, transaction, then suspended that program, and execute some commands from the next program, and so on. A program is resumed at the point where it was suspended when it gets its turn to use the CPU again. This is known as interleaving. Now let's look at interleaved versus simultaneous concurrency. If the computer system has multiple hardware processors, CPUs, simultaneous processing of multiple programs is possible, leading to simultaneous rather than interleaved concurrency. Genuine versus appearance of concurrency. Concurrency is the ability of the database management system to process more than one transaction at a time. You should distinguish genuine concurrency from the appearance of concurrency. The database management system may queue transactions and process them in sequence. To the users, it will appear to be concurrent, but for the database management system it is nothing of the kind. This is discussed under serialization below. Now, let's discuss about the read and write operations. At this level, the database access operations that a transaction can include are: read item X reads a database item named X into a program variable also named X. Write item X writes the value of program variable X into the database item named X. Executing a read item X command includes the following steps. Find the address of the disk block that contains item X. Copy the disk block into a buffer in main memory if that disk is not already in some main memory buffer. Copy item X from the buffer to the program variable named X. Executing a write item X command includes the following steps. Find the address of the disk block that contains item. Copy the disk block into a buffer in main memory if that disk is not already in some main memory buffer. Copy item X from the program variable named X into its correct location in the buffer. Store the updated block from the buffer back to disk, either immediately or at some later point in time. Let's look at the lost update problem. Lost update problem occurs when two transactions that access the same database items have their operations interleaved in a way that makes the value of some database item incorrect. That is, interleaved use of the same data item would cause some problems when an update operation from one transaction overwrites another update from a second transaction. Uncommitted dependency or dirty read or temporary update. Uncommitted dependency occurs when a transaction is allowed to retrieve, or worse, update a record that has been updated by another transaction, but has not yet been committed by that other transaction. Because it has not yet been committed, there is always a possibility that it will never be committed, but it will be rolled back instead, in which case the first transaction will have used some data that is now incorrect, a dirty read, for the first transaction. Let's look at inconsistent analysis. The inconsistent analysis occurs when a transaction reads several values, but a second transaction updates some of these values during the execution of the first. Another problem that may occur is the unrepeatable read, where a transaction, T1 reads an item twice, and the item is changed by another transaction, T2 between reads. Hence, T1 receives different values for its two reads of the same item. Phantom record could occur when a transaction inserts a record into the database, which then becomes available to other transactions before completion. If the transaction that performs the insert operation fails, it appears that a record in the database disappears later. Need for recovery. Whenever a transaction is submitted to a DBMS for execution, the system is responsible for making sure that either all the operations in the transaction are completed successfully and the effect is recorded permanently in the database, or the transaction has no effect whatsoever on the database or on any other transactions. Transaction problems. There are a variety of causes of transaction failure. These may include concurrency control enforcement. Concurrency control method may abort the transaction to be restarted later because it violates serializability, the need for transactions to be executed in an equivalent way, as would have resulted if they had been executed sequentially, or because several transactions are in a state of deadlock. Local error detected by the transaction. During transaction executions, certain conditions may occur that necessitates cancellation of the transaction. Example, an account with insufficient funds may cause the withdrawal transaction from that account to be cancelled. This may be done by a programmed abort in the transaction itself. A transaction or system error due to some operation in the transaction may cause it to fail, such as integer overflow, division by zero, erroneous parameter values, or logical programming errors. User interruption of the transaction during its execution, example, by issuing a Control-C in a VX, VMS, or Unix environment. Other transaction problems are system software errors that result in abnormal termination or destruction of the database management system. Crashes due to hardware malfunction, resulting in loss of internal, main, and cache memory, otherwise known as system crashes. Disk malfunction such as read or write malfunction, or a disk read or write head crash. This may happen during read or write operation of the transaction. Natural physical disasters and catastrophes such as fires, earthquakes, or power surges, sabotages, intentional contamination with computer viruses, or destruction of data or facilities by operators or users. Desirable properties of transactions: acid, atomicity, consistency, isolation, durability. Where atomicity. A transaction is an atomic unit of processing. It is either performed in its entirety, or not performed at all. A transaction does not partly happen. Consistency. The database state is consistent at the end of a transaction. Isolation. A transaction should not make its updates visible to other transactions until it is committed. This property, when enforced strictly, solves the temporary update problem and makes cascading rollbacks of transactions unnecessary. Durability. When a transaction has made a change to the database state and the change is committed, this change is permanent and should be available to all other transactions. Serializability. This is a criterion that most concurrency control methods enforce. Informally, if the effect of running transactions in an interleaved fashion is equivalent to running the same transactions in a serial order, they are considered serializable. We have used the word schedule without a definition before in this unit. In this section, we will first define the concept of transaction schedule, and then we characterize the types of schedules that facilitate recovery when failures occur. Schedules of transactions. When transactions are executed concurrently in an interleaved fashion, the order of execution of operations from the various transactions forms what is known as a transaction schedule. In a serial schedule, entire transactions are performed in serial order. T1 and then T2, or T2 and then T1 in Figure 9.9a. Serial schedules are considered correct. Schedules C and D in Figure 9.9b are called non-serial because each sequence interleaves operations from the two transactions. Non-serial schedules with interleaves of operations may result erroneous in database. Serializable schedule. Schedule S of n transactions is a serializable schedule if it is equivalent to some serial schedule of the same n transactions. A serializable schedule gives us the benefits of concurrent execution without giving up any correctness. Now, let's discuss about locking techniques for concurrency control. One of the main techniques used to control concurrency execution of transactions, that is, to provide serializable execution of transactions, is based on the concept of locking data items. A lock is a variable associated with a data item in the database and describes the status of that data item with respect to possible operations that can be applied to the item. Types of locks. There are several types of locks can be used in concurrency control. Binary locks, shared and exclusive locks. Use of the locking scheme. To see in more details, click on it. Binary locks. A binary lock can have two states or values, locked and unlocked, or 1 and 0 for simplicity. A distinct lock is associated with each database item, X. If the value of the lock on X is 1, item X is locked and cannot be accessed by a database operation that requests the item. If the value of the lock on X is 0, item X is unlocked and it can be accessed when requested. We refer to the value of the lock associated with item X as lock X. Shared and exclusive locks. A read locked item is also called share locked because other transactions are allowed to read access that item, whereas a write locked item is called exclusive locked because a single transaction exclusively holds the lock on the item. If a DBMS wishes to read an item, then a shared S lock is placed on that item. If a transaction has a shared lock on a database item, it can read the item, but not update it. If a DBMS wishes to update an item, then an exclusive X lock is placed on that item. If a transaction has an exclusive lock on an item, it can both read and update it. Use of the locking scheme. using binary locks or multiple mode locks in transactions, as described earlier, does not guarantee serializability of schedules in which the transactions participate. For example, two simple transactions T1 and T2 are shown in Figure 9.13a. Assume initially x equals 20 and y equals 30. The result of serial schedule T1 followed by T2 is x equals 50 and y equals 80. And the result of serial schedule T2 followed by T1 is x equals 70 and y equals 50. Figure 9.13b shows an example where, although the multiple mode locks are used, a non-serializable schedule may still result. The reason for this non-serializable schedule to occur is that the items y in T1 and x in T2 were unlocked too early. To guarantee serializability, we must follow an additional protocol concerning the positioning of locking and unlocking operations in every transaction. The best-known protocol, two-phase locking, is described next. Guaranteeing serializability by two-phase locking, 2PL. Basic 2PL. A transaction is said to follow the two-phase locking protocol. Basic 2PL protocol, if all locking operations, read lock, write lock precede the first unlock operation in the transaction. Such a transaction can be divided into two phases. An expanding or growing phase, during which new locks on items can be acquired, but none can be released. And a shrinking phase, during which existing locks can be released, but no new locks can be acquired. Dealing with deadlock and live lock. Deadlock occurs when each of two transactions is waiting for the other to release the lock on an item. Conservative 2PL. A variation of the basic 2PL is conservative 2PL, also known as static 2PL, which is a way of avoiding deadlock. The conservative 2PL requires a transaction to lock all the data items it needs in advance. If at least one of the required data items cannot be obtained, then none of the items are locked. Rather, the transaction waits and then tries again to lock all the items it needs. Although conservative 2PL is a deadlock-free protocol, the solution further limits concurrency. A simple way to detect a state of deadlock is to construct a wait-for graph. One node is created in the graph for each transaction that is currently executing in the schedule. Whenever a transaction, Ti, is waiting to lock an item, X, that is currently locked by a transaction Tj, create a directed edge, Ti of Tj. When Tj releases the lock on the items that Ti was waiting for, the directed edge is dropped from the waiting for graph. We have a state of deadlock if, and only if, the wait for graph has a cycle. Figure 9.16 shows the wait for graph for the partial schedule shown in Figure 9.15. Ordering data items deadlock prevention protocol. One way to prevent deadlock is to use a deadlock prevention protocol. One such deadlock prevention protocol is used in conservative 2PL. It requires that every transaction lock all the items it needs in advance. If any of the items cannot be obtained, none of the items are locked. Rather, the transaction waits and then tries again to lock all the items it needs. Let's discuss about wait die and wound wait deadlock prevention protocol. Suppose that transaction, Ti, tries to lock an item, X, but is not able to, because X is locked by some other transaction Tj, with a conflicting lock. The rules followed by these schemes are as follows. Wait die. If Ts, Ti, Ts, Tj, Ti is older than Tj, then Ti is allowed to wait, otherwise abort Ti, Ti dies, and restart it later with the same timestamp. Wound wait. If Ts, Ti, Ts, Tj, Ti is older than Tj, then abort Tj, T-wound Tj, and restart it later with the same timestamp, otherwise T is allowed to wait. Moreover, in wait die, an older transaction is allowed to wait on a younger transaction, whereas A younger transaction requesting an item held by an older transaction is aborted and restarted. The wound wait approach does the opposite. A younger transaction is allowed to wait on an older one, whereas an older transaction requesting an item held by a younger transaction preempts the younger transaction by aborting it. Live lock. Another problem that may occur when we use locking is live lock. A transaction is in a state of live lock if it cannot proceed for an indefinite period while other transactions in the system continue normally. This may occur if the waiting scheme for locked items is unfair, giving priority to some transactions over others. The standard solution for live lock is to have a fair waiting scheme. One such scheme uses a first-come first-served queue. Transactions are enabled to lock an item in the order in which they originally requested to lock the item. Another scheme allows some transactions to have priority over others, but increases the priority of a transaction the longer it waits, until it eventually gets the highest priority and proceeds.